All right, so we are going to be moving on to note 21. This is all about continuous probability distributions. So just a super general thing, it's pretty much the same as discrete. There's just one thing that we're going to cover in the beginning that separates it. But it's really much of the same. So yeah, we've been dealing with discrete probability distributions. Our random variables have been able to take on finite or countably infinite values, but in reality, there are many cases in which the probability distribution will be continuous. For example, what is the probability that a particle is in a specific position or maybe area in a box or a cube? And that might give you a hint as to how continuous is different from discrete. But all right, so we're going to go into continuous uniform probability space. So the Wheel of Fortune example, a lot of things kind of go back to this. So let's look at it. So pretend that we spin a wheel and we want to know the probability that we land at a particular point in that wheel. We're going to let L be the circumference of that wheel. So, like the border, the length of the border. So we're going to translate this to discrete probability, where we're going to assume that there are m points on the circle, each with equal probability. Circle, we can think of it as having infinitely many points. So as m gets really large, we get closer to the continuous case, right? But if m is infinite, then the probability of landing on a particular point becomes 0, right? And that's not very helpful for us. So in the continuous case, what we do is we use a range. We fix two values, a and b, and we say that it's somewhere between like 0 and L, and we assert that b has to be greater than a. And so if we want to find the probability of us landing in a particular point, then we would say b minus a divided by the entire sample space, which is L. And this is an event, or a subset of points in our sample space. So the probability of disjoint union events, let's say we have the probability that we are in the first quadrant, so maybe like say 12-3, and then the probability that we're in the third, which would that be 6-9? I don't know if first and third would be the right way of thinking, but if you think of a clock like 12-3 and then 6-9, those each cover like 1/4 of the area. So 1/4 out of the entire area plus 1/4 out of the entire area. I mean, visually you can see that that's half of the entire sample space. Okay, so now we're going to move on to continuous random variables, and we're going to define this thing called a probability density function, which is a real valued random variable that is a function which maps values from the real numbers to the real numbers, and it satisfies these two conditions. F has to be non-negative, greater than or equal to 0, and the total integral of f is equal to 1. And total refers to negative infinity to infinity. Okay, and the distribution of x is given by the integral from some point a to some point b, such that b is greater than a. And the probability of x being in a set of real numbers is this integral. So it's equal to 1 over the entire possible interval. And we can kind of compare this to our Wheel of Fortune example. So we know that over the entire span, this is just kind of follows from our definition, like 1 equals this. And if we think about, if we have values that are negative, that's obviously not going to be on our circle. If we have values that are larger than our circumference of L, that's also not going to be on our circle. So our random variable f of x looks like this. It's 0 for anything less than 0, and it's going to be 1 over L for anything between 0 and L. And so again, and same for it's 0 if it's greater than L. So something important to note is that the only thing that says that this has to be equal to 1 is when we're integrating from negative infinity to infinity. Because in this case, if we treat L as 1 over 2, then f of x is going to be equal to 2 in this case. So essentially what we're saying is that we can't simply evaluate our function at a particular point, because that doesn't represent the probability. Again, this is a probability density function, right? So, but what does represent a probability is when you take the integral of f over a certain range. And just if we make the change from x to x really small, then we can approach a value that would be like we were evaluating f at x. Kind of calculus like stuff. But yeah, something that they use to refer to this is the probability per unit length. Again, not per specific point, but per unit length essentially. So now we're going to move on to cumulative distribution functions. So basically what it is this capital F of x is equal to the probability that x takes on some value less than or equal to x. So we have our point in the sample space, and then we want to know the probability of anything less than or equal to that point. And naturally that looks like this, and we can obtain f of x by, what would we be doing? Evaluating the integral. So taking the derivative of this. I think it's one of the fundamental theorems of calculus. And we can see that the probability of x being, let's see this, x, so x of j being less than some x being less than or equal to like a slight increase in x of j is approximately just equal to evaluating f at x sub j. So this is saying the probability that x takes on a value that's basically x sub j is approximately this. Again, it's like as we're making the bounds or the range as small as possible, we converge to a specific point, which is x sub j. I feel like this is sort of straightforward. And so if we want to do it for everything that is less than or equal to some x of I, then we would sum up all of those points that are less than or equal to I, and we would evaluate it there. And that's pretty much how that works. Okay, we're going to go into the expectation and variance of this. So the expectation of a continuous random variable x with probability density function f is as follows. Again, if we think about the discrete random variable, what that is taking the sum of the expectation of, the expectation of a discrete random variable is the sum of multiplying what the value the random variable takes on times the probability that it takes that on. So again, in this case, x is that value, f of x is, us inputting that into our random variable. So if we look at the wheel example, the expected value of x, we're going to take the integral from 0 to the circumference. That's just going to be x times 1 over L. Again, we're ignoring the spots outside of the values confined in our circumference, and just taking the integral with respect to x, we get x squared over 2L, and then just evaluating it, we get L over 2. Okay, next we're going to go over the variance of this. So just kind of algebraically, we remember variance takes on this form, which it's much easier to do things when we put it in this form, and we already calculated the expectation. It's this, so we can just square this entire thing. And then the expectation with x squared is simply just squaring the values that x takes on, but not changing the probabilities that x originally takes on when we put it through this function. Like we wouldn't square f of x, we would just square x squared. Okay, and then again just doing some calculus, I guess. Yeah, we would raise x to, or take the integral, raise this divided by 3, we get this, input L, and then we would input 0, and we would get L squared over 2, which would give us, L over 2 squared, and I think from here, let me just take a closer look at this. Right, so again, we had already calculated the expectation of x, so squaring that is just going to look like L over 2 squared. Now all we have to do is take the integral of, the expectation of x squared, and so that's going to look like this. Taking the integral with respect to x, 1 over L is a constant, so x to the 2, we just, raise it to the next power, and then divide by that power, and then we have to evaluate it at L and 0, and that just gives us, what is it? L to the 3, which there's an L on the bottom, so that gets canceled out, and so we just have L squared over 3, and we subtract that by squaring this, and that gives us L squared over 12. I think we actually do this in a discussion too, like 12b or something. So next we're going to go on to joint distributions. So, the probability of 2 events happening. So for discrete random variables, we're going to say the variable x is equal to sum a, and the variable y is equal to sum c for all possible values of a and c. So this is kind of what the joint distribution between 2 discrete random variables is. But for the continuous case, again, we have to kind of look at a range of values. And we pretty much just replace this with, okay, so x is going to take some values between, or some value between a and b, and then y is going to take some value between c and d, and we're just going to say for all a, b, c, and d, such that these conditions are true. I think that's fairly straightforward, probably more straightforward than me explaining it. But now we're going to go into the formal definition, and so it's a function r squared because we have these 2 inputs, we have the x and the y, or we're dealing with 2 independent variables. And we need f to be non-negative. It takes, x and y is greater than or equals 0 for all x and y in the real numbers. And the integral, the total integral, so it's like this double integral where we're taking it from negative infinity to infinity with respect to x and y, that has to be equal to 1. Yeah, I guess taking multivariable would have helped. Yeah, maybe should have done that in the first place, but anyways, so yeah, the joint distribution is given as follows. It follows pretty much directly from here, for all a and b and for all c and d. So if we want to find the probability kind of at a particular x and the probability at a particular y, we would again have to evaluate it at a range, but if we make that range small enough, then we can get to what is approximately evaluating f at x and y. So, just following this formula, just plugging this in, we would get an approximation for what f of x at y is equal to. Okay, and then we're going to talk about independence. So again, for discrete random variables, they are considered independent if x is equal to a and y is equal to c are different for all possible values of a and c. So again, just the discrete case, we look at a point. The continuous case, we look at a range for our random variables. We're going to say that two random variables are independent if it is the case that for these ranges, you know, a and b for x and c and d for y, if the probability is equal to the probabilities of them separately and then just multiplied together. And then we'd kind of do the exact same thing we did up here. For small enough change in x, we can essentially figure out what it is like to evaluate x at that particular point. And in this case, this probability right here is considered the marginal density of x, like probability density of x. And then similarly, f of y is marginal probability density of y. Marginal being it's like confined to just that random variable. And let's see, the joint density of independent random variables x and y is the product of the marginal densities. Right. Yeah. Okay. So let's move on to some distributions, some new distributions, although fairly familiar, I would say. So this exponential distribution looks a little bit different, but is in a way, well, if you look at it from a different point of view, I guess, it is like a continuous version of the geometric distribution. So formally, for lambda greater than 0, a continuous random variable x with probability density function f of x is going to look like this. It's called an exponential RV with parameter lambda, and we write it as x is equal to exp to lambda, right? So it's 0 for any negative number, and for any non-negative number, it's lambda times e to the negative lambda x. So again, f of x is non-negative, and we can see that it's a valid distribution. Just take the integral from negative infinity to infinity. We know everything below 0 is 0, so we can just take it from 0 to infinity. Taking the integral, we would essentially just be dividing by negative lambda. And if we look at what that is, you could pull up Desmos. You would see that as it goes to infinity, it actually converges to 0, and when you evaluate it at 0, you get 1. But again, it's going to be 0 minus 1, and so that gives us 1. And this is just kind of a chart for the distribution. So it's kind of like it's a decay, it kind of decays. And naturally, we're going to talk about the mean and the variance. So we're going to use integration by parts, which I don't think this is quite right. Integral of u. Yeah, honestly, I don't remember it exactly from Calc BC. I need to refresh my memory. But, okay. Let's see if we can get through this, though. So, again, expectation is going to take this form just for continuous random variable. And we know that anything below 0 is just 0, so we can take it from 0 to infinity. And here is where we apply the integration by parts bit. So I think we have to pick a u. Yeah, we pick like a u and a dv, and then we have to obtain the du and the v from that. So if we pick, let me see, I should have written this down. Okay, so I've written it out here. Integration by parts uses this formula where the integral of u times dv is equal to uv minus the integral of v du. So that means we have to find a u and a dv in this equation, and we want to pick those values such that, for at least for the dv, when we integrate it to get v, that should simplify it. And similarly, when we take the derivative of u for this part, it should also simplify it. That's just like a general rule. I'm sure you probably know that, but I needed to refresh myself on that. So anyways, if our equation takes this form, then our u is going to be x, and our dv is going to be e to the negative lambda x, I believe. Does this lambda just get taken out, though? I am a bit confused as to where the lambda goes. So if u... Well, okay, so if u is equal to x and e to the negative lambda x is equal to dv, then when we take the integral of d and du. Oh, okay, so yeah, I'm not actually too sure. Hold on. Okay, I should have done this from the beginning, but just to go over it all again, and we're spending too much time on this, but again, our integral takes this form. We're going to set our u to equal x. We're going to set our dv to be equal to what's left over, so lambda e to the negative lambda x. And that means that our du is going to be 1, taking the derivative of x with respect to x is going to yield 1, and taking the integral of this is going to equal negative e to the negative lambda x, because we just kind of bring this down and divide by it. So just kind of subbing things in, we have our u here, and then we have our v here, and then we have our v by itself, and then the du, which is just 1, and then notice this is negative, but in the actual formula we also have a negative, so this negative comes out and makes this positive. And then let's see, this term becomes 0, this term becomes this, and as we run to infinity, that's going to make this top term 0, but then evaluating it at 0 is going to yield 1, so we just get 1 over lambda. Okay, I'm probably not going to go as in depth with the other calculus proofs in this note, but just for the sake of time. So yeah, so now we need to calculate the variance. We've already calculated the expectation by itself, so squaring it is easy. Now we have to calculate the expectation of x squared. So we pretty much apply the same ideas. We're going to evaluate from 0 to infinity. We're going to sub in our values for f of x, and we're going to choose the proper values for u and dv, and then we're going to get this, and then we know that what the actual variance is. It's this minus this squared, and so that's how we get 1 over lambda squared. So this is the variance, and the mean is 1 over lambda. So a continuous time analog of geometric distribution. To be honest, I didn't entirely understand this one. I don't know if just the algebra is getting sort of mixed up for me, but I'm going to do my best. So again, if we think about what the geometric distribution is, it's, what is the probability that our random variable is greater than or equal to some t, let's say. And basically we translate that to, what is the probability that the first time that we land on heads is, say time t. Well, that would require every I guess flip, if we're using the coin flip analogy, that would require every previous flip before t to be the probability of getting tails. So yeah. And we're going to look at what this looks like in the exponential case. So just taking this integral and evaluating it from t to infinity, the probability that it's greater than t is just going to give us this. We're going to just kind of plug it into the formula that we're given, and we're going to get this value right here. And probability, so what this is saying is the probability that we wait more than time t is equal to e to the negative lambda t. And as we saw here, it sort of decays as lambda gets, or as time goes on. So now they kind of introduced a couple different terms to try to relate it to the geometric distribution. And this one, delta, is going to represent time per trial of, some event. And then p is the probability of success. And then we're going to assert that lambda is going to be the fixed rate of success per unit of time, right? It's just literally just success over time. And then we're going to have a discrete variable y, which is going to be the time until we get a success. Okay, so we're going to say the probability that y is equal to some multiple of, our time is just going to be equal to 1 minus p to the k. So it's like getting tails k times. And we can sub in p, for p, we can sub in lambda times delta. And this holds for positive t and for positive k, or non-negative k, I guess. And so if we say, what is the probability that our discrete random variable y is greater than t, is going to be the same thing as if we just algebraically manipulated it to look like this. And from there, we can sub in. Yeah, I think this is sort of where I was getting lost, but this kind of takes that form, k. So yeah, I guess so k is this multiple right here, and if we literally just sub in k for that, then I think we sort of just accept that this looks like this form. And again, lambda is equal to this. Yeah, I think the algebra is sort of where I got lost, unfortunately. But we can interpret lambda as the success rate per unit time, and see how it plays an analogous role to p, the probability of success of each trial. Yeah, I wish I could offer a better explanation, but it's not really that solid for me, unfortunately. Okay, so let's just move on to normal distribution. So you might be familiar with this. I never took a stats class, but I'm sure they went over this distribution in that class. So just to define it, for any mu in the set of real numbers and any sigma greater than 0, sigma referring to standard deviation, a continuous random variable x with probability density function of this form is called a normal random variable with parameter mu and sigma squared. And we can write it as this. In the special case where the mean is equal to 0 and the standard deviation is equal to 1, x is said to have the standard normal distribution. I think I wrote that again, but just to check that it's a valid distribution, take the integral from negative infinity to infinity, and I think this is just left as an exercise, or it's just assumed that we've done it in multivariable, but I haven't taken multivariable, so I'm going to accept that that is the case. And then this lemma right here sort of, yeah. So I understand what it's saying. I'm just having trouble applying it, which is the unfortunate part. But basically what this says is that any discrete or any continuous random variable that is some sort of normal distribution can be represented as some other continuous random variable that takes the original random variable, subtracts out the average, and divides by the standard deviation, and this random variable will take on the form of the standard normal distribution. And then also, if we have something that is equal to the standard normal distribution, then we can take x's standard deviation, multiply it by this standard normal distribution random variable, and then add the average, and then we'll get our normal distribution. So we can calculate the distribution of y is equal to x minus mu over sigma as this. So taking the probability over this range for y is going to be the same as taking the probability over this range for x. We're just kind of using this formula right here. And so substituting in the normal distribution formula, we're going to plug in for our bounds sigma a plus mu on the bottom and sigma b plus mu on top. And if we sort of just evaluate this, or let's see, yeah, if we were to evaluate it, I believe the terms would just cancel out and we would be left with, or no, sorry, we don't have to evaluate it. We can simply just sub back in what this is in terms of y. So again, this is x minus mu over sigma. That takes this same form. So this becomes y there, and then this in like the y, I guess, universe looks like this, and as we sort of saw from this equation. So that's pretty much what we do. So yeah, again, y is the continuous random variable that takes on this standard normal distribution, this easy to look at, like this one right here, this blue curve, this nice centered around 0. The mean is centered around 0 and it has that standard deviation of 1. Yeah, hopefully, I feel like me explaining it honestly makes it more complicated than what is actually going on, but hopefully you get the gist. So let's go over the mean and the variance. So let's see, we just establish or just assert that the mean of x, such that it's a normal distribution, is equal to mu, and the variance of x is equal to sigma squared. I really think that, is it a sigma? The other one was delta, so this has to be a sigma. Yeah, okay. So let's see, negative infinity to infinity. Again, we're going to use that same formula for continuous random variables, taking the expectation of continuous random variables, plugging this in, substituting in values. Something that we can note is if we take the integral from negative infinity to 0 of this integral, it's going to be the exact same as taking the integral from 0 to infinity of this integral, because this is symmetric around 0. So the area under the curve on the left side of 0 is the same as the area under the curve for the right side. And so that is what we get. Yeah. Okay, and then I think, was this the exact same thing? Yeah, I think it is. Okay. The variance, so we got the expectation, now we just have to square this inside. Let's see. So we do integration by parts again. So we know that the expectation is 0, so square that, we get 0. In this line, we do integration by parts. I'm not going to go over it. And then we notice that let's see. Oh yeah, so once we perform integration by parts, we get down to this form, because this, I believe, just goes to 0. And this takes on this same special form right here. And we know that this has a, what is it? How do we know that it's equal to 1? Because we're taking the integral from -infinity to infinity of this, which is the probability density function for a standard normal distribution. So we know that this has to be 1. Okay, and so let's see. I think this is just another way of looking at it. So again, we assert that the expectation of some x for for just any normal distribution is 0. As we see from here, you see over here. Anyways, let's see. Expectation is mu. Okay, so yeah, so if we say that 0 is equal to the expectation of like the standard normal distribution, just subbing in this right here, we kind of get this expression up here, which again just evaluates to 0. And then if we assert that the variance of x is equal to sigma squared for x, well, we know that the variance of y has to be 1. So again, just subbing in x minus mu over sigma for y, we obtain this form, and given that variance of x over sigma squared has to be equal to 1, then we can see that the variance of x is also the same. And just in a general sense, the probability that x is less than or equal to some a is equal to probability that y is equal to, or y is less than or equal to this form, which we're just kind of relying on this equation that we've seen a couple times now. This one right here. It's probably worth memorizing or having on your cheat sheet. So what we aim to show by stating this is that we can obtain information about any normal curve by using this formula. Viewing its offset from the standard normal. And do we just have a bunch of pictures? Or we have a couple? Okay, I'm going to try to get through this a bit quicker, but okay. So we're going to go into the sum of independent normal random variables, and this one's a bit math heavy, so hopefully I can explain this. But so we're going to assume we have two random variables. They're both going to have the standard normal distribution, and they're both going to be independent. And we're going to assert that there is this random variable z that's equal to a of x plus b of y. And what we're going to assert is that the normal distribution of z is has a mean of 0 and a variance of a squared plus b squared. So how are we going to show that? By this theorem, we know that their joint densities are simply the result of multiplying their individual PDFs by each other. So they both take this form, 1 over 2 pi e to the negative x squared over 2 for x, and then it's a y squared over 2 for y, so we just kind of multiply them together, and then we get this form. And there's this function. This is the function that we get for the joint densities of these two. And notice that it's rotationally symmetric around the origin. So if 0 is here and then 0 is here, I think I wrote it down here. Imagine we have like a point there, and then we have like a pole that goes through the center. If we rotate this graph around that pole, nothing is going to change in terms of area, and that's kind of what this t is. So we're going to say that the probability that x and y takes on some value in some space A is going to be the exact same as if we were to translate it, or apply t to A. And maybe translate isn't the right word, but all t is doing is rotating r squared, this xy plane, essentially. So yeah, so we're going to assert that the probability that z is less than or equal to t is just the probability of ax plus by, as we defined up here, that's less than or equal to t. And that is really the same as the probability that x, y is in A. And A, to account for these, this A and this B that are multiplying our x and y, we're going to assert that A is this half plane in xy, such that ax plus by is less than or equal to t. So yes, so taking a look at what that looks like graphically, given that these are the values that z can take on, and they have to be less than or equal to t, we're going to see that, you know, we're basically, the xy plane is infinite, right? And we're just kind of dividing it at a specific point, and we see that the distance from the origin at which we're dividing it, like this right here, is some value d. And so if we literally just take it and then we transform it or translate it and then make it vertical like this just makes our calculations a lot easier, and we maintain this distance of d. And that's kind of what this is saying, that we can just translate it. And therefore, all this area is going to be the area that is less than or equal to this t over the square root of a squared plus b squared. And yeah, so the transformation of a is equal to that, and this pretty much summarizes all of it. Probability that z is less than or equal to t is the probability that our random variables x and y that make up z fall within A. And again, A is this space right here, but that's the same as if we were to translate A, or rotate, I guess. Rotate is really what we're doing, which is algebraically equivalent to if we were just evaluating the probability that our random variable x takes on some value, you know, less than or equal to this wall, essentially. And just using some manipulation, we're going to throw this up here, and we're going to see that the probability that the square root of a squared plus b squared times x is less than or equal to t is the same as this. Okay, so z has the same distribution as a squared plus b squared times x, and the mean is 0 and the variance is a squared plus b squared. And this is by lemma 21.1, and to be honest, I think I brought it up, what is it? I understand the purpose of this, but I'm not really sure how we got what we got from lemma 21.1, like how this arises out of that. And then also there's this corollary which kind of generalizes, but I'm not going to go over that. I'm running very low on time, unfortunately. Okay, so the central limit theorem, let's see. we brought it up in earlier note, but essentially by making our number of samples large enough, we can make the error between our measured probability and the true probability as small as possible. So that should hopefully be familiar. And we're going to define some terms right here. So we're going to have some independent indicator random variables, and then we're going to have our random variable s of n, like some sample something, be the sum of those independent indicator random variables. And dividing this by n is going to be the average of our sample. So the central limit theorem states that the distribution of s of n over n for large enough n looks like the standard normal curve. So we, standardizing this so that it's constant and not dependent on n. Honestly, not too sure how this works. This definitely looks like the lemma 21.1 formula. Yeah. And that gives us this. So I guess this puts it in this sort of standard, yeah, that's literally what it's doing, like puts it in the standard normal distribution form. And that sort of brings us to this definition, which puts everything together. So we have our indicator random variables, and we're going to set or say that the expectation of each of those random variables is equal to mu, and that they each have a finite variance conveniently of sigma squared. And we're going to assert that our sample random variable is going to be equal to the sum of those indicator random variables, and then the distribution of this converges to the normal distribution. So honestly, I would probably look up a video, like a YouTube video on how this works. And I'm not sure if this is actually what this is saying, but like intuitively, I think this is what it's saying. Like I should probably like understand what I'm talking about before I make a whole video on it, but for the sake of getting through material, I'm just gonna say what I thought this kind of represents. So take this with a grain of salt, definitely. I think what it's saying is if we take an average of n observations for our random variable x, then if we have a small number of observations, then the distribution of the average of our observations, like our expected probability, that's not going to be very large because we don't have very many samples. But as we hit sort of like our mean, as we have a large, like a medium number of samples, then there's a potential for a wide range of, distribution of averages. And then as n approaches infinity, the distribution becomes very close to what the actual probability is. So if we think of this in terms of a biased coin, we don't know what the probability of landing on heads is, and we want to measure that by flipping the coin. If we've only flipped the coin like once or twice, then there's not going to be much variation in what our measured probability is. But if we flipped it, say maybe 10 times, maybe that's closer to what our mean is, and so we have a potential for a wide range of predicted probabilities, right? We could have only landed on heads once, and so we could think that the probability is 1 over 10, or we could have landed on heads 10 times, and so we think the probability of landing on heads is 10. But as we flip the coin a ton of times, like thousands of times, millions of times, then statistically we should be converging onto the actual probability of landing on heads for that coin. Okay, so that has been a very quick note 21. Actually, I don't think that was very quick, but for the amount of material covered in this note, I think it was. So yeah, that has been continuous probability and distribution. No, continuous probability distributions, right?